Howdy folks, welcome back. So in this video, I'm just going to quick go through the practice quiz and again show you how I go about solving the problems. Again, I recognize this by no means the only way, and in some cases it might not be the way that works best for you. But if you're curious as to where to start, this just kind of gives you an idea as to how I would go about solving the problems there. Right? So again, in this quiz, we are looking mainly at Markov processes. So with these Markov processes, we have these transition matrices. So for example, here we have for a certain group of states, it was observed that 70% of Democratic governors were succeeded by Democrats and 30% by Republicans. Also, 40% of Republican governors were succeeded by Democrats and 60% by Republicans. All right, so this means that my transition matrix would look something like this. So again, we have the transition from the states along the columns to the states along the rows. So the transition from Democrat to Democrat is going to be 70%, as given in the problem there, and from Democrat to Republican is going to be 30%, or 0.3, again, as given by the problem. All right, so here we're asked for an initial distribution of 40% Democrat and 60% Republican. What is prediction for the distribution after the next election? All right, so again, this represents my matrix A, and then I have my initial distribution is 40%, 60%, which is going to be 0.4, 0.6, and again, we represent that by, so our initial distribution, we represent that by a subscript 0. All right, so then to find my next distribution, so the distribution after one election, I'm just going to take A times my initial distribution in this case. All right, so you have 0.7, 0.4, 0.3, 0.6. We're going to multiply that times 0.4, 0.6. All right, so that's just a matter of doing the matrix multiplication. All right, so again, you march across the rows of your first matrix down the column of your second matrix. So we have 0.7 times 0.4. 0.7, oh, help if I turn the calculator on. So we have 0.7 times 0.4, and I'm going to add 0.4 times 0.6. 0.4, 0.6. All right, so you have 0.52. And for the second row, again, I'm going to march across the second row and again down my column. So you have 0.3 times 0.4 plus 0.6 times 0.6. And again, you should end up with something that adds together to equal 1. So if you end up with your final answer and the entries don't add together to equal 1, that means that you probably made a mistake somewhere along the line there. In this case, we're going to take 0.52 plus 0.48. We do end up with 1. So that kind of passes the quick check there. All right, and then we represent this by 1 since this is after one election. All right, so that is my final answer. All right, so the next problem, so we're given a regular stochastic matrix below. So again, stochastic matrices need to have the columns adding together to equal 1. They need to be entries in between 0 and 1. And for a regular stochastic matrix, some power or some exponent of that matrix has to have entries that are all greater than 0. All right, so in this case, this matrix raised to the first power contains all entries that are greater than 0. So this would be an example of a regular stochastic matrix there. All right. So then to find my stable distribution, so if you have a regular stochastic matrix, those have a stable distribution. So my distributions are going to look something like X, Y, and Z here. And you represent this by big letter X. All right. So my stable distribution, to find that, I would solve the following system of equations. So first of all, the entries in X have to equal 1. So the sum of the entries in X have to equal 1. So you have X plus Y plus Z has to equal 1. And when you transition from one stable matrix to another, it doesn't change. So stable matrix remains the same there. All right, and again, to find your transition, you're just going to take A times X. All right, so for the first row, We're going to use the first row of A, and again, march down the columns of X here. So we have 0.3X plus 0.1Y plus 0.2Z. All right. And again, that has to equal my matrix X. So the entry in the first row of X is X. So this has to equal X. Right, so then for the second row, again, we're going to take the second row of my transition matrix and march down the column. So we have 0.4X plus 0.8Y plus 0.6Z. And that has to equal the second row of my stable distribution. So that has to equal Y. All right, and then for the final row here, we're going to use the final row of my matrix A, and again, march down the column. So you have 0.3X plus 0.1Y plus 0.2Z. And that has to equal Z. All right, so that is my system of equations that I would need to solve in order to find my stable distribution. So that's all that problem is asking for. So you don't have to go through and solve everything. Yeah, when you have 3 variables, that can get very complicated in a hurry. So yeah, so I'm just asking for the system of equations, so something like that. All right, and the final problem here is dealing with the absorbing states. All right, so yeah, so we're asked for the absorbing states for the matrix below. So again, those absorbing states are states where once you enter into that state, there's no escaping that given state there. All right, so for example, again, we have transitioning from the states along the columns to the states along the rows. All right, so here we have the transition from state A to state A is 100%. So once it arrives in state A, it's going to stay in state A. So yeah, so that would be an example of an absorbing state there. Likewise for state B, so here we have once you arrive in state B, we have a 100% chance of staying in state B and a 0% chance of going elsewhere. So that would be another absorbing state. All right, so again, you might be tempted to say, okay, so if you have a 1 in one of your rows, 0s everywhere else in that column, that automatically makes an absorbing state, which isn't quite necessarily true. All right, so for example, here we have a 1 in one of my rows and 0s everywhere else in the C column. All right, but the 1 is in the transition from state C to state D. So in this case, it's leaving that state, so that means that that would not be an absorbing state there. Likewise, here we have the transition from state D to state C. So again, it's leaving state D, so it's just constantly going to be flipping back and forth between C and D, which means that neither of those are going to be absorbing states. So in this case, I just have 2 absorbing states of A and B. All right. So yeah, so again, this is just kind of a side question. This is actually going to be a question on the quiz. But would this be an example of an absorbing stochastic matrix? So in this case, again, in order to be an absorbing stochastic matrix, you need to be having at least one absorbing state. So it has that, but you also need to be able to get to one of those absorbing states from any other state in your given scenario. All right, so if we start in state C or D, there's no way that we can get to states A or B or my absorbing states. So this would actually not be an example of an absorbing stochastic matrix. It still has some absorbing states, but it's not going to be an absorbing stochastic matrix. All right. So yeah, so again, that's just how I go about solving problems. Again, I recognize it's by no means the only way, and in some cases it might not be the way that works best for you. But if you're curious as to where to start, hopefully that gives you a little bit of insight as to how I go about solving problems there. Thank you very much. Have a lovely day, and I'll talk to you all later. Bye now.